Hello again. This time we're going to go over some Lewis diagrams, which is another way of creating the structure of a compound and illustrating the valence electrons instead of all the electrons like you guys did in Bohr diagrams. So this should be a little bit more simplified than what you're used to for Bohr diagrams. I'm going to go and skip to the page where there's some practice for Lewis diagrams. Here we go. So I'm going to go through some of these Lewis diagrams, and again, if you need extra help on this, please approach us during flex time or look for some examples of these drawings online. Here we go. So sodium. If you look at your periodic table, sodium is in the first family, which means it has a valence electron of 1. So all I'm going to do is draw the symbol Na, and I'm going to draw a dot. It doesn't really matter which side you put the dot on, as long as there's one dot on one of the sides, because there's only one valence electron. So that was pretty easy. Let's go on to silicon. Silicon, which is Si, has, if you look at the family, it's family number 14, which means it has 4 valence electrons. So usually, never eat shredded wheat. You basically go in compass direction, and that's just a way of spreading out your electrons, and that's typically how you would draw Lewis diagrams. So 1 on each side, spread it out before you start pairing. And in this case, it doesn't lap around a second time, so there are no electron pairs here. Let's go on to chlorine. So for chlorine, it has 7 valence electrons according to the periodic table. So I'm going to start here and go around. And then you'll notice that you do a second lap. And on the second lap, you pair up the electrons until you have 7 electrons in the valence shell. So you see 3 lone pairs of electrons and then 1 electron to the side. And it really doesn't matter which side you end up on with that 1 electron. But when we do draw compounds, it most likely, well, it will end up on the side where you're going to form a bond. Lithium. Let's take a look at lithium. It's in the first family, so that means lithium also has just 1 valence electron, and I'll just put it on the top. Now let's look at some compounds. Now there are 2 types of compounds. One type is called ionic, and another type is called covalent. The only difference between these two is that ionic bonds are formed by electrons being transferred and then the resulting ions being attracted to each other because they have opposite charges. Covalent compounds share electrons. It's a much stronger bond, but the electrons are shared and it follows the octet rule. So you really need to figure out when you're drawing compounds whether, first of all, it's ionic or covalent. BeS, which is beryllium sulfide, to figure out whether this is ionic or covalent, you look at the 2 pieces here. So Be and S. Be happens to be a metal. It is on the left side of the periodic table where the metals are. S, sulfur, is a nonmetal. So here we have a metal with a nonmetal, and so a metal with a nonmetal would form an ionic bond. A nonmetal with a nonmetal will form a covalent bond. So since this is an ionic bond, we expect to see charges, which in Lewis diagrams we will indicate by using square brackets. So Here we are going to put Be in square brackets and then indicate the charge on the outside to the top right. So for beryllium, it's 2 plus. So the ratio is 1 to 1, so there is no coefficient before the Be or the S. So for the sulfur, we're just going to draw another square bracket. And during the process of creating this compound, beryllium, as indicated by the 2 plus, gave up its 2 valence electrons. So that's why when we draw Be, the symbol Be, we didn't put any electrons around it. It's given those 2 up. Where does it go? Well, it pops onto the sulfur. So sulfur will take those 2 electrons to form an octet. So it'll fill up its outer shell. Sulfur normally has 6 valence electrons. So 6 plus 2 from beryllium gives you 8. So we're going to draw sulfur here with 8 electrons around it. Okay. Finish off the square bracket and then indicate sulfur's charge, which is 2 minus, which means that it took 2 electrons from beryllium. Let's take a look at the next one. Magnesium fluoride. So for magnesium fluoride, is this an ionic compound or is this a covalent compound, covalently bonded compound? If you look at the 2 parts, magnesium is a metal, fluorine is a nonmetal. So we have metal with a nonmetal, so this is an ionic compound. So for this ionic compound, again, we're going to put the metal in brackets, square brackets, and indicate the charge on the outside, 2 plus. Now in this case, the ratio is MgF2. So we're already given the compound formula, which shows that ratio. If you're just given a name, you'll just have to figure out what the ratio is by drawing the compound formula. In this case, the compound formula is already given. So we know there are going to be 2 fluorine atoms. So we put a coefficient of 2 on the outside, on the left, and draw fluorine. So these 2 fluorines, each fluorine will take 1 electron away from magnesium. So that's why magnesium has no electrons around it. So the Lewis structure for fluorine has 7 electrons around it, plus 1, then you have 8. So each fluorine takes 1 electron, two of those will take 2 electrons. So that is the Lewis diagram for MgF2. Let's look at diatomic chlorine. Now, if you remember back to all of the diatomic compounds, the diatomic compounds are forming a number 7 on your periodic table in the nonmetals. So you can go back to make sure you've labeled all of the ones that are part of the diatomic compounds that form diatomic compounds. And chlorine is one of them. So diatomic chlorine means chlorine exists as Cl2 in nature, which is a gas. So because it's a nonmetal, and it's nonmetal with itself, so this would be a covalent compound. So when we form a covalent compound, the first step would be to write the symbol Cl, and then it's going to form a bond with itself. So we're going to draw that first line. Now, in the end, each of these 2 atoms has got to follow the octet rule. So each chlorine has 7 valence electrons. So that means if we go 1, 2, 3, 4, 5, 6, and the 7th one being here, then it's going to share, and that's going to become 8. So it's actually going to be 1, 2, 3, 4, 5, 6, 7, 8. Same thing with this one. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So in this bond that's formed, there are 2 electrons being shared, and plus the other ones gives you 8 for each chlorine, and that follows the octet rule. Okay, so let's take a look at phosphorus trifluoride. Okay, so anytime you have a name that includes all those Greek prefixes like tri, di, mono, you know that it's a covalently bonded compound because that's just how you name it. You use those Greek prefixes. Plus, you can look at phosphorus and fluoride, and both of those are on the right side of the periodic table. They're both nonmetals, so it must be covalently bonded. Okay? So it's trifluoride, so there's 3 fluorides and 1 phosphorus. So let's start off by drawing phosphorus in the middle, and we've got 3 fluorides surrounding it. So I'm just going to draw lines for each fluoride. That's how we're going to start this. And then we're going to figure out how the electrons are shared. So in phosphorus, we should have 5 valence electrons plus 3 fluorides. Each fluoride has 7 valence electrons. 3 times 7 is 21, plus 5 is 26 electrons. So let's just make sure we have 26 electrons at the end. So in fact, when these are covalently bonded, the electrons can transfer to all of these. They're all shared. But let's start with the bonds that we drew. Phosphorus needs to have 5 valence electrons around it, or starts with 5 valence electrons. So let's say this is 1, 2, 3, 4, 5. Okay? So if we left it like this, it would then have 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, and then 7, 8. Okay, so that follows the octet rule. Let's make sure fluorine also follows the octet rule. So fluorine has 7 electrons valence. So 1, 2, 3, 4, 5, 6, and the 7th one is making a bond with phosphorus. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that works for fluorine. So then we can finish this off by just drawing the remaining lone pairs of electrons for all the fluorines. Okay, so the number one thing is to make sure all of the atoms follow the octet rule, which in this case it does. Phosphorus does, and all 3 fluorines follow the octet rule as well, which means 8 electrons around it. Okay, diatomic oxygen. So diatomic means there's 2 oxygens bonded together. So we're going to start it off by going like this, O2, and then we'll try to make it follow the octet rule. So oxygen has 6 valence electrons. So 1, 2, 3, 4, 5, and then 6 is in the bond already. 1, 2, 3, 4, 5, and 6 is in the bond on this side already. Does that equal 8 for each of these? So let's go 1, 2, 3, 4, 5, 6, 7. No, it does not. So let's see what we can do. what if we took one of each of these electrons at the bottom here and put those together? Would that be 8? So I'm going to quickly erase these two. Why is this not erasing? Okay. And then we'll form a bond with those two. So now if we count on the left one, we got 1, 2, 3, 4, 5, 6, 7, 8. That's good. Right side, 1, 2, 3, 4, 5, 6, 7, 8. So counting the ones that are in the bond, we have 8 electrons for each oxygen. So this follows the octet rule. Perfect. Next one, carbon dioxide, CO2. So because there are 2 oxygens, I'm going to suppose that carbon lands in the middle, and then we'll put oxygen on either side, and we'll draw a bond because we know there's going to be at least one bond. And let's see what happens. Okay, so carbon has 4 valence electrons, so there should be 2 more here. Well, that 1, 2, 3, 4, 5, 6, that doesn't add up to 8. So something else needs to happen. So what if we took these 2 electrons on carbon and made bonds with them with oxygen? So now we have double bonds. Well, in this case, if we count all the electrons that are shared in those 1, 2, 3, 4 bonds, then we have 8 for carbon. 1, 2, 3, 4, 5, 6, 7, 8. 8 bonds, 8 electrons are being shared for carbon. Let's finish off the oxygens now. So if oxygen has 6 valence electrons, then we've got 1, 2, 3, 4, 5, 6, and then 7, 8 in the bond. So this works out for oxygen. So it should be exactly the same on this side too. Okay, so now each oxygen has 8 electrons. Or the carbon in the middle also has 8. So that's it. Thank you for watching.